Lorscheid, and he'll be giving part 2 of this. Motivation is representability of matroids over fields. We all know that that's interesting, but there's also things like partial fields in the sense of Semple and Whittle, and I'll be talking about an even bigger generalization here today. Now, the kind of thing I'm after is there's a construction of Rudy Peneving and Stefan von Swalm where they introduced something called the universal partial field of a matroid. And the universal partial field governs, in a certain precise sense, all of the representations over all partial fields. So this is interesting and it has some nice applications, but there's some problems here. For example, by Peter Nelson's theorem, asymptotically 100% of matroids are not representable over any field, and therefore not over any partial field as well. Remember, I'm talking about commutative partial fields today, not skew partial fields. It's not hard to see that if you're representable over some partial field, you're also representable over some field. So for 100% of matroids, asymptotically speaking, there is no universal partial field. It's just not defined. And so, I mean, the theory is very interesting in certain cases, but it doesn't really tell us about most matroids. So I'm going to describe a generalization today called the foundation of a matroid. And the advantage is that, one advantage is that it exists for every matroid. Okay, it's always defined. And it's definitely interesting when M is not representable over any field, but it's also interesting when M is representable over fields, because assuming it's representable over certain fields, you get information about representations over other kinds of objects. And for example, the kind of thing we can handle here is we can say things about reorientation classes, which is something in the theory of oriented matroids. And we're able to study such questions in exactly the same way as one typically studies representations over partial fields. Right, now, in order to get there, we'll need to do a couple things. So as I said, we have to generalize the notion of field, first of all. And then it's sort of important that we take a sufficiently abstract point of view on representing matroids that we don't talk about matrices. I mean, you can write down matrices if you want, but the usual way of defining representations and studying them is not really conducive to this kind of generalization. So I'll define representations and say things about them without ever talking about matrices. Okay, and so the key generalization of fields that I want to tell you about is something called pastures. So in addition to telling you what pastures are, I'm going to tell you about representation of matroids over pastures. And in particular, we'll have certain rescaling classes. These basically correspond to projectively equivalent representations in matroid theory. And then we have this foundation, F sub M, which generalizes the universal partial field, and it has the property that the rescaling classes of a matroid over a pasture P are in one-to-one correspondence with homomorphisms from the foundation to P. All right. All right, I'll assume everyone can still hear me unless you tell me to the contrary. So now for the generalization of fields. So the main idea is we want to give up, and we have to give up something if we're going to generalize something else. The thing we're going to give up is that addition comes from a binary operation. Okay, so a field is one way of thinking about it. You have an abelian group with respect to multiplication. And then you have some additional element called 0, which absorbs everything multiplicatively. And then there's another operation called plus, which for a field is a binary operation. And it's defined on k star together with 0. And then, of course, there's some axioms. So what we do with pastures is we still have a multiplicative abelian group, P star. We still have an absorbing element 0. And we still have some kind of additive structure, but we don't require that there's a binary operation that gives rise to it. So there's two examples to keep in mind if you want to understand this. Okay, one is actually partial fields, which for people in this audience is probably the easier example, but I tend to think of that as the second example. So the other example I want to explain first is hyperfields. So let's just start with this hyperfield. It's the simplest one that isn't a field. It's been called the Krasner Hyperfield. So what it is you have, the abelian group is trivial. It just has one element 1, and then you add a element 0, and this gives you a multiplicative monoid, right? So 0 times anything is 0, and 1 times 1 is 1. And now you have some additive relations, which is that 0 plus x is x, 1 plus 1 is 1, and 1 plus 1 is also 0. Okay, so if that looks strange, well, you might, it's because you're thinking of plus as a binary operation, right? It's not, doesn't have just one value here. It has 2 values. Or better yet, we just say that both of these relations are true. 1 plus 1 is 1, and 1 plus 1 is 0. So, right, that's what I just said. And although this may seem counterintuitive, if you think of 1 as just a formal symbol that means not 0, then 1 plus 1 could either be 1 or 0, because the sum of 2 non-zero things could be 0 and it could be non-zero. And I claim, and we'll see this later, that this is really closely related to Matroid theory, where in some sense, right, when we have a vector space or a matrix, we sort of just care whether certain things, let's say certain determinants or certain linear combinations are 0 or whether they're not 0. And that's all that matters for a Matroid. And so some of the Krasner hyperfield is secretly underlying a lot of aspects of Matroid theory. Okay, and then the other example that people here will probably know is the regular partial field. Now in the literature, like in von Zwaan's thesis, this is called U0, but for reasons that I probably won't explain today, I'm going to call it F1 plus or minus. But it's the same thing. So it consists of 0, 1, and -1 with the usual multiplication. And then the additive relations are that 0 plus x is always x, and 1 plus -1 is equal to 0. What's missing here is there's nothing, like 1 plus 1 is not equal to anything. So you could just say that 1 plus 1 is not defined. But again, it's just better to say there is no relation of the form 1 plus 1 equals x in this pasture. So again, this additive structure does not come from a binary operation, but here it's not for the same reason. 1 plus 1 isn't defined, rather than in the previous case, it was multi-value. And if you understand this, then pastures, just kind of the minimal structure in which that includes both of these examples in a certain sense, and includes fields. Okay. So, right, and this kind of, you can think of this as encoding arithmetic in the ring of integers, but you're restricting to a certain multiplicative subset. Okay, so to unify these two examples, what do we do? So pastures have involutions, which we'll write as x goes to minus x. That's needed for various things in the theory, including when you axiomatize determinants, you really have to have a minus sign, and it comes up all over the place. So we want this involution. But notice that the involution x goes to minus x might be trivial, like in the Krasner Hyperfield or in the field of two elements. And so the idea is that we're going to rewrite x plus y equals z as x plus y plus negative z is equal to 0. And in that way, we can always write things as three-term relations, and we just want to know whether a certain additive combination of three elements is 0 or not. And so these additive relations, a plus b plus z equals 0, are supposed to be symmetric with respect to a, b, and c. So I'm going to identify them with triples, which will be invariant under symmetries. So the set of all such triples a, b, c, such that a plus b plus z is 0, is called the null set of the pasture. Okay, so that's just notation, but formally, what is a pasture then? So it's a multiplicative monoid with 0. 0 is supposed to be an absorbing element. So that when you remove 0, you get an abelian group. You have an involution, x goes to minus x, which fixes 0. And then you have a subset of triples with the following properties. So first of all, as I said, it's supposed to be invariant under permutations. There's a kind of weak distributive law, which is if you multiply each of a, b, and c by the same non-zero scalar, then whether a plus b plus c is 0 or not doesn't change. And 0xy is in the null set if and only if y is equal to minus x, where this minus x means the involution. So in other words, 0 plus x plus y is null if and only if x plus y is null if and only if x equals minus y. So these are all kind of reasonable axioms I think you would admit, and that's it. That's the only axioms we have in a pasture. It's fairly permissive. And just to compare it to the other notions, it's convenient to introduce this notation, but we'll never use it again in the talk after this slide. You can write x box plus y, that's the latex symbol there, is the set of z such that x plus y minus z is equal to 0. So that's like, if it were a binary operation, this would be just x plus y. Z would be equal to x plus y, but in general, it's a set, maybe empty. So a pasture is a field if and only if this box plus operation here is an associative binary operation. And if it contains at least one element for all x and y, and it's associative in a certain sense, then that gives you what is classically in the literature called a hyperfield. So hyperfield, these hypersums have to be non-empty. On the other hand, if the box plus contains at most one element for all pairs and satisfies some associative law, then P is called a partial field. And this coincides with the usual notion of partial field. Once you make the associativity precise, that's actually not obvious how to do it. And so the idea here is that pastures, we simply have no conditions on the size of these sets x box plus y, and no associativity conditions at all. And it turns out that simplifies a lot of constructions, in fact. So Anton says, are there some natural non-associative examples? Yes, I mean, in the sense that once you start allowing empty sets, this operation to be empty, it becomes less clear what you mean by associativity, and depending on how you define it, it's sort of easy to write down natural examples that aren't associative in any obvious sense. So, okay. Now, I don't strictly need this for too many things, but I think it's important to sort of understand where hyperfields come from in nature. So the simplest example is you start with a field K, and a multiplicative subgroup of K star. Let's call it G. So then you can look at K mod G, right? And what is that? Well, one way to think of it is you just take the quotient group, K star mod G, and you formally adjoin 0. And this naturally has the structure of a hyperfield. Was there a question, or was that just someone unmuted? All right, I'll assume that was not a question. So the additive relations here, if I denote by bracket x the coset of x, or the orbit under G of x, then x plus y is equal to z if and only if there's some scalars a, b, and c, so that ax plus by is equal to cz. So that's just the only natural thing you could possibly do to try to make an additive structure, put an additive structure on this quotient set. And if you do this, for example, with the reals modulo the non-zero reals, that gives you the Krasner hyperfield, right? Because you've got the orbit of 0 and the orbit of 1. Those are the only two orbits under R star. And the addition law I gave you before is exactly fits with this quotient construction. There's nothing special about the real numbers here. You could have taken any field, except maybe the field of 2 elements. But basically any field would work here. However, the real numbers are interesting because of the next example. In the real numbers, you could also, instead of quotienting out by R star, which is disconnected, you could take the connected component of the multiplicative identity element 1, which is the positive real numbers. And now the reals mod the positive reals has 3 elements represented by 0, 1, and -1. And that's called the sign hyperfield. And then there's all kinds of other interesting examples you can write down. I won't really need them in this talk, so I'll just go through this quickly. For example, if P is a prime number congruent to 3 mod 4, then you could take FP mod FP star squared, and that actually doesn't depend on which prime you chose. And that's called the weak sign hyperfield. Or you could take the complex numbers mod the positive reals, and that's called the phase hyperfield. And I mean, there's lots of examples like this. But here's the thing, not every hyperfield arises as a quotient of a field. And in fact, my student Tong Jin and I have a recent conjecture that it's sort of like Peter Nelson's theorem, but in the context of hyperfields, that asymptotically 100% of all finite hyperfields are not quotients of fields. Right, so this is the obvious source of hyperfields and the motivation for them, this quotient construction, but in fact, I conjecture that there are lots of hyperfields out there that aren't of this type. Okay, but they're all pastures. And now let's talk quickly about partial fields. So for those of you that haven't seen it, or maybe if you have, putting it in this language might be illuminating. Suppose you have a commutative ring R, and now you have a subgroup of the multiplicative, of the unit group of R, and it contains -1. So now we're sort of restricting to a subgroup rather than quotienting out by a subgroup. So it's in some sense a dual operation. And you just take the group together with 0, and this has the structure of a partial field where the additive relations are just the ones that hold in the ambient ring. But the elements of your partial field are just the elements of the subgroup together with 0. And this forms a pasture. But this is a bit different because actually every partial field has this form. So it's not as subtle as the hyperfield case. Okay, now to give some examples of partial fields, it's convenient to use this notation. If R is a commutative ring, P of R will be the partial field corresponding to the units of R inside of R. Right, so in general, you could take a subgroup of R star, but I want to take G equal to R star. And so if you apply this construction to the ring of integers, you get the regular partial field that we saw before. And if you apply this construction to z adjoin 1/2, right, where you allow denominators that are powers of 2, you get what's called the dyadic partial field. And you could also take z adjoin a primitive 6th root of unity. And then you get what Oliver and I call the hexagonal partial field. I think it has a different name in some of the Matroid theory literature, but we had to avoid some conflicts of notation. So we call it H. And then we have what's called the near regular partial field, where you take z adjoin x, 1 over x, and 1 over 1 minus x, where x is an indeterminate. And you take the units of that ring inside that ring, and that gives you the regular partial field. Okay, you'll see where these things come up later. I'm not going to actually talk much today about cross ratios, but that'll be a big part of Oliver's talk next week. And you can see that this partial field U is intimately connected with cross ratios, because these are the kind of expressions that appear when you start looking at cross ratios. Or maybe it's not obvious if you haven't seen this before, but trust me, U is naturally related to cross ratios of 4 points on a projective line. Okay, pastures form a category. So a homomorphism is basically what you would guess if I just didn't tell you anything. It's a multiplicative homomorphism of the underlying groups, which extends to 0. So it gives you a map of monoids. And it should also take 1 to 1. And then whenever you have an additive relation in P, F should map it to an additive relation in P prime. So it's just the usual definition of a map that preserves all of the structure that we have. Nothing surprising here. Oh, and I guess I should have said it preserves the involution too. Maybe that follows though. It probably follows from the axioms. Anyway, if it doesn't follow, then add that condition. So pastures form a category whose initial object, Oliver says, yes, it follows. Okay, so that's why we left it out. So pastures form a category whose initial object is this regular partial field and whose final object is the Krasner Hyperfield. Right, so if you're not a category theorist, this just means that there's a unique map from the regular partial field to any pasture, and there's a unique map from any pasture to the Krasner Hyperfield. And we'll see that we can define matroids over pastures, and when we do, matroids over the initial object are regular matroids, and matroids over the final object are just matroids. We also have other nice structures that will come up later. We have sort of arbitrary limits and co-limits, but the only thing we'll use in this talk are products and tensor products. And I'll just point out that, I mean, these are, this is actually a really nice advantage of pastures over even the category of fields, and definitely over partial fields and hyperfields, because none of those have both products and co-products, and we use both of them in our work. Okay, so now comes the link to Matroid theory, and as I said, I need to now tell you what a representation of a matroid over a pasture is, and I don't want to define it in terms of matrices. So instead, I'll define it in terms of determinants of matrices without using determinants or matrices, right? So you have this axiomaton, you have this kind of set of axioms that determinants of maximal minors of matrices satisfy. They're called the Plucar Relations in algebraic geometry. And they come up in the theory of the Grassmannian. So we're mimicking that. And this is not new to us. This kind of idea is been around for a long time. So M is a matroid of rank R on a finite set E, and P is a pasture. And I want to tell you what a P representation of M is. It's going to be a function from R tuples of elements of the ground set into P, such that first of all, think delta is like a determinant here. Delta is non-zero if and only if this R tuple is a basis of your matroid. Second, it has this alternating property that determinants have. So if you apply a permutation to the columns, let's say, if you want to think of it that way, it just changes the determinant by the sign of the permutation. And then finally, these Plucar relations. So the Pluco relations say if you have a R minus 2 tuple J and 4 more elements, then you can add those 4. There's 6 ways to add in 2 of those 4 elements. And depending on how you do it, you have some signs showing up here. And you get these Plucar relations. And again, these relations are satisfied by the maximal determinants of maximal minors of a matrix of rank R. So I hope people are familiar with this. But if not, it's just some algebraic relation between determinants. We're only looking at the 3-term relations here, though. In my paper with Nathan Bowler, that some of you may know and others not, I'm not assuming it here, but we look at arbitrary size Plucar relations. But I don't want to do that today. So what I'm doing today corresponds to what Nathan and I call weak matroids. Oh, and we also look at things called tracts, which are slightly more general than pastures, in that you can have relations that are more than 3-term. Here we only have 3-term additive relations. But again, for studying representations of matroids, the 3-term relations are the easiest ones to deal with and the ones with the most structure. So that's why I'm doing this. Okay. So, whoops, I must have skipped. Oh no, that's right. So that's what a representation of a matroid is. I think it's on a later slide, but I'll just say now, if P is a field or more generally a partial field, you can check that a matroid, a representation is just a certain isomorphism class of P representations. Probably should have put that slide next, but I think I put these out of order. So actually, let me go to the next slide and then come back. So we'll say that M is representable over P if there's at least 1 P representation. 2 representations, delta and delta prime, are isomorphic if there is some non-zero scalar C, so that the 2 determinant-like functions differ by a multiplication by that constant. And so a weak P matroid in the sense of my paper with Nathan is just the same thing as an isomorphism class of P representations of that matroid. Okay, so now let me go back to these cryptomorphisms. I'm going to go through this quickly too, because I don't really need it for this talk, but I mean, I think it's important for various things, and it's used in some of the proofs. So you can also describe, I just use determinant-like functions. But you can also use circuits. So here's another way to characterize P representation. So suppose M is a matroid, P is a pasture. P representations are the same thing as functions from the circuits to P to the E. Such that, first of all, the support, so called the function rho, if you take the support of rho, so P to the E means, maps from E to P. It's like it would be a P vector space if P was a field. The support of rho of a circuit C should be just C. So you're basically, for each element E of your ground set, you're giving coordinates. So for each circuit, you're giving coordinates, and the eth coordinate is 0 if and only if E is not in the support of that circuit. And then you have some kind of strong modular circuit elimination property. I think in the interest of time, I might skip this. Again, I'm not going to use it today, but here it is, and you can see it in my paper with Nathan or my paper with Oliver if you're interested. But it's a natural condition. And similarly, there are bijections between P representations of M. In pairs of functions, you're sort of coordinatizing both the circuits and the co-circuits of your matroid in such a way that you preserve the supports. And if you have a circuit and a co-circuit with at most 3 elements in common, then the dot product of these corresponding vectors is 0, where the dot product is just the sum in the pasture. And since we have at most 3 elements in common, that's a 3-term additive relation. And so it makes sense to ask whether it's 0 or not. Okay, and it just occurs to me there might be a subtlety with isomorphism classes of these things versus the individual things. I know the isomorphism classes of all these things are in bijection, but I wrote something slightly stronger and I'm worried that might not actually be true. What's the meaning of rho for a representation over a field? Right, so rho would be, for example, if the circuits correspond to a minimal linear dependence between the columns of some matrix, then you're just specifying what the coefficients of that minimal linear dependence are, right? And those are entries of your field. And then if you just remember which ones are 0 and which ones are not, that gives you the circuit, the corresponding circuit of the matroid. Good question. Okay. So what we're really interested in today are rescaling classes of representations rather than isomorphism classes. So this is a equivalence relation that identifies more things together than just isomorphism. So the abstract definition is that 2 Grassmann-Plucar functions, delta and delta prime, are rescaling equivalent. If there's a constant C, that's like the previous constant, and also a map D from your ground set to P star, so that so now you're not only allowed to multiply by the constant C, but you can multiply by a scalar, a non-zero scalar for each element of your ground set E. And so we call such things rescaling equivalence. This is the analog of projective equivalence for representations of matroids over fields, if you know what that is, or of reorientations in the theory of oriented matroids. So we'll write script X superscript I to denote isomorphism classes of P representations, and superscript R to denote rescaling classes. All right, so I already mentioned this. If K is a field, then if you have a K representation, as I just defined it, of a matroid, it comes from a matrix representation in a certain obvious sense, namely that delta is then the determinant of the maximal minors of that matrix. I mean, this is basically the statement that I'm familiar with in the context of algebraic geometry, but it's just a linear algebra fact that every alternating non-degenerate function satisfying the Plucar equations actually comes from a matrix. And that's what you need to show that the Grassmannian is defined by the Plucar equation. Except there's a subtlety here in that we're only using 3-term relations, and I don't want to get into that, but that's an interesting subtlety. But what I wrote here is true. let's see. Over the Krasner hyperfield, every matroid has a unique representation. Okay. So in particular, I mean, the thing to keep in mind is now we've made every matroid representable, right? There's always at least one pasture over which any matroid is representable, namely the Krasner hyperfield. In extreme situations that might be, well, I think it's never the only pasture because you can embed K inside other pastures as well, but sometimes there's not many other hyperfields or not many other pastures over which a given matroid might be representable, but at least there's always one. And if P is a partial field, then matroid is representable over P in the sense I just defined, if and only if it's representable by a P matrix in the sense of Penavang and Van Zwan. So in particular, that means that a matroid is regular if and only if it's representable over the regular partial field. Now, a regular matroid in general has lots of non-isomorphic representations, but they're all rescaling equivalent. So there's a unique rescaling class of representations over the regular partial fields. So that's another reason to introduce rescaling classes, is it helps with the study of regular matroids, but it helps with lots of other things too. And finally, I sort of mentioned this before, matroid is orientable in the usual sense of oriented matroid theory, if and only if it's representable over the sign hyperfield that I introduced before. And orientation is the same thing as an S representation. And rescaling equivalence is usually called reorientation equivalence. So now for one of the main theorems, at least abstractly, but my goal is actually to tell you some much more concrete things that you might care about even if you're only interested in representations over things like fields. But a key fact is that given a matroid M, there's a functor that takes a pasture P to the set of isomorphism classes of representations over P. And that functor is representable by something that we call the universal pasture, P sub M. If you're not up on your category theory, what does that mean? It means that there's a natural isomorphism between isomorphism classes of representations over P and homomorphisms from the universal pasture into P. But what we'll really be interested in this talk is a certain subpasture of the universal pasture called the foundation. And this represents the functor taking a pasture to the representation classes, sorry, the rescaling classes over P. So rescaling classes correspond to homomorphisms from the foundation. All right, this theorem is not hard to prove, but I'm not gonna do it. What's difficult is to describe the universal pasture and the foundation in concrete terms that you can calculate and prove theorems about. But it's not hard to just abstractly prove that it exists. Maybe I'll quickly mention, I think I mentioned already that when the foundation is a partial field, it coincides with the universal partial field in the sense of Penavang and Van Zwan. That's true. And also, what was I going to say about that? So they don't ever say in their papers, though, that you have this natural isomorphism between rescaling classes and homomorphisms from the universal partial field. I'm not sure if that wasn't known before or just wasn't written down or what, but anyway, it's just very natural in our context to say this. And it works very nicely. And that one-to-one correspondence with homomorphisms will come up soon when we talk about unique representability. So some general properties of these things. So let me just focus on the foundations, but you can read the statements about universal pastures if you want. So the foundations of M and its dual are canonically isomorphic. That's not hard to see. If you have a minor given explicitly as, where you delete I and contract J, then the foundation of N maps naturally to the foundation of M. So there's kind of functorial behavior with respect to minors. And if you just look at the multiplicative groups of the universal pasture or the foundation and forget the additive structure, it recovers what's called the Tut group or inner Tut group, introduced by Dress and Menzel. And so in a sense, if you like, what we're doing is endowing their theory with a bit more structure, not just looking at groups, but at these pastures. And that actually has a lot of useful consequences, though, and cleans things up quite a bit, in my opinion. They just don't have the language to talk about representing functors. And their notion of fuzzy ring is more complicated than the notion of a pasture. Okay, so now, yeah, one more categorical thing, and then I'll actually tell you some facts about representations of matroids. So just by the universal property of a product, M is representable over both P1 and P2, these are pastures, if and only if it's representable over their product. And this actually can be used to prove theorems in matroid theory, as you'll see in a minute. But coproducts are useful too. Coproducts in this case are the same as tensor products. The foundation of a direct sum is canonically isomorphic to the tensor product of the foundations. And this is also true, but slightly less obvious for two sums, which is also pretty interesting and an open problem that Oliver and I are very interested in, that we'd love some help from people that really know matroid theory well, is to try to characterize precisely when the foundation of a matroid breaks up in a non-trivial way as a tensor product of foundations of other matroids, for example. Yeah, Oliver might say more about this next week. I don't want to say more about that now. But it should be related in some complicated way to three connectivity. Okay, now what can we do with all of this? Why is this not just abstract nonsense? Well, in the theory of partial fields, you already have interesting arguments like the following. Right, so if you take the product of F2 and F3, and by the way, F2 here means what matroid theorists would typically call GF2, the finite field of two elements. This is just the way algebraic geometers tend to write it. So if you take the product of F2 and F3 as pastures, you actually get the regular partial field. That's just a simple computation, I guess. And so, I mean, this gives a very clear, concise proof of the theorem that a matroid is representable over every field if and only if it's regular, in the sense of being representable by a totally unimodular matrix. Yeah, I mean, I could give more details here, but I think a lot of people probably know this. If not, it's just an exercise, given what I've said. But you can do other things. For example, Whittle proved that a matroid is representable over F3 and F4 if and only if it's hexagonal, or a sixth root of unity matroid, which means representable over H. Yeah, so these kind of things are well known. But the theory of pastures is much more flexible. So let me give you an example. So here's something you can't do with partial fields. Right, so the product of the finite field of two elements and the sign hyperfield is also the regular partial field. That's just another easy computation. And so the same argument that we used before gives you that a matroid is regular if and only if it's both binary and orientable. And although that's a known theorem, I'm not sure if it was known that you could give a unified proof of that and Tutt's theorem that, you know, work in the same way. And now what's really interesting is when you try to, I mean, this is all pretty elementary, but if you try to use other pastures, I mean, these are very small pastures and their products are simple to work out. In general, you run into some interesting complications. So for the last 10 minutes of the talk, I'll give you the following key example. So this is kind of the illustrative test case that got us started working on all of this seriously on this latest project. So there's a theorem of Lee and Scoby that a matroid is ternary and orientable if and only if it's dyadic. Okay, now this would not be provable within the usual theory of partial fields because the orientable is not expressible without using hyperfields, I think. So here you need a category that contains hyperfields and partial fields, which pastures does. But the product trick doesn't work anymore. Right, so F3 cross S, you might hope was just isomorphic to D and that was the proof, but it's not true. D is the dyadic partial field. But it is true that there's a homomorphism from D to the product, but it's not an isomorphism. Okay. So the theorem of Lee and Scoby is actually deeper than the previous theorems. What you have to show is that any homomorphism from the foundation of a matroid to F3 cross S lifts to the dyadic partial field. So in particular, that means that F3 cross S can't be the foundation of a matroid. But how would one show that, right? I mean, how would you show something is not a foundation? We need to know some structure theorems for foundations of matroids, some useful descriptions of them. And so Rudy Peneving told us where to look for that with this theory of the inner Tutt group and just descriptions in terms of generators and relations. And so that was the key breakthrough that allowed us to do things like proving the theorem of Lee and Scoby from this point of view, and then lots of other similar theorems follow as well. Just for the experts in the audience, this is closely connected to what Peneving and Van Zwijm call the lift theorem. So this is how they would resolve that kind of difficulty in the context of partial fields. So we need a kind of generalization of the lift theorem, which we used Tutt's homotopy theorem and variants of it by the authors I wrote down. And I mean, what we get in the end is that a homomorphism from the foundation of some matroid to F3 cross S not only lifts to the dyadic partial field, but it lifts uniquely. And I believe that uniqueness was not known before. So we get an additional statement here about some kind of unique representability. So more precisely, we also generalize this beyond just ternary matroids, although it's really almost the same statement, that if you have a matroid without large uniform minors, that means minors that are isomorphic to either U25 or U35, then this is true. The map D to S induces a bijection, Hom from the foundation to D to Hom foundation to S. Right. So how does that work? So the main theorem of this talk is the following. So that what I just said is a simple consequence of a classification of all possible foundations of matroids without large uniform minors. Right, so we can say something about matroids which have U25 or U35 minors, but it gets a lot more complicated, as many of you know. And probably if we make some weaker assumptions, we can still prove things, but we're still working on this kind of thing. But we get a very clean, nice statement if we assume that there are no U25 or U35 minors. And here's the statement. So if you have such a matroid without large uniform minors, then its foundation is a tensor product of certain building blocks. And the building blocks, there's 5 basic building blocks. And there are these things I've already written down, the near regular partial field U, the dyadic partial field, the hexagonal partial field, the field of 3 elements, and the field of 2 elements. But keep in mind that once you start taking tensor product of these things, you leave the world of partial fields. So I think you really need pastures to make these kind of statements. And so how would you prove the Lee-Scoby theorem once you know this, this theorem here? Well, if you want to show that some homomorphism to S lifts uniquely to D, if the foundation is a tensor product, then the universal mapping property of tensor products shows that you can just check that statement for each building block separately. And so now you just have 5 concrete partial fields, and you want to check whether each homomorphism to the sign hyperfield lifts uniquely to the dyadic partial field or not. And that's just something you can check with your bare hands. It's very simple. So the deep fact is really this classification theorem, and then the rest follows. So a paper is like, I don't know, 80 pages long or something, but a lot of that is just mining this theorem here for consequences, and the rest is sort of proving this theorem, which takes some work. But let me just quickly, in the 3 or 4 minutes I have left, give you a few consequences. So yeah, I mean, the consequences, you can just kind of, you could almost like program a computer to just generate consequences of the structure theorem, because now it's all about just whether certain pastures admit homomorphisms to other pastures or not, or whether certain lifts are unique. And you can just kind of make tables of these things and generate theorems. So what kind of theorems could we prove? And actually, let me skip this one because this is a little bit more nuanced, in fact, but you can actually prove something about positively orientable matroids. Let me skip that. Yeah, so let me say this instead. The representation class is just the set of all pastures over which M is representable. And 2 matroids we'll call representation equivalent if they're representable over exactly the same pastures. So the theorem is, if you have a matroid without large uniform minors, then there's exactly 12 possibilities for its representation class. And of these, 9 are representable over some field and the other 3 are not. So this is sort of something that, well, I don't know how you would even formulate a theorem like this without using something like the theory I'm introducing here, because your matroids aren't representable over any fields. How would you distinguish 3 different classes of such things? Maybe there's a way to do it, but this is, it's very natural from our point of view to find these 12 classes. And you also get a bunch of uniqueness results basically from these, yeah, I mean, from the things I've said. Lee-Scoby is a kind of unique lifting result, but you also have the following. If you have a ternary matroid, maybe I'll finish with this slide, then up to rescaling equivalence, every representation over F4, the field of 4 elements, lifts uniquely to the hexagonal partial field. So again, I think this is, it's known that every representation lifts. I'm not sure whether or not it was known that lifts uniquely. Anyway, if that is known to the experts here, our methods give a new proof of this. Similarly, every representation over F5 lifts uniquely to the dyadic partial field. Every representation over F7 lifts uniquely to D tensor H. Every representation over F8 lifts uniquely to the near regular partial field. Again, these things just, you can just churn out theorems like this, although they would get harder to state. And maybe you lose uniqueness at some point. I'll finish with this slide, last slide. here's one more fun thing you can do. And I'm curious if this is known to the experts or not, even without the uniqueness part. So suppose you have a ternary matroid and you have two prime powers, P1 and P2, such that this funny expression Q is also a prime power and it's not a power of 3. Then you actually get an identification between rescaling class spaces. So the rescaling equivalence classes of representations over FQ, they correspond to pairs of rescaling classes over the field of P1 elements and rescaling classes over the field of P2 elements. So you get really funny theorems like this, just to give you an example. So if you have a representation class, projective representation class over F4 and one over F5, those are in one-to-one correspondence, those pairs with projective equivalence classes over F8. And similarly for F17, F5, and F7, or F47, F7, and F11. Presumably there are infinitely many examples like this, but that's a number theoretic problem that looks pretty hard. So I think I'll stop there and see if there are any questions.
Thank you, Matt. Unfortunately, it's a bit harder to clap in this, but thank you for the great talk. Are there any questions?
I have a quick question. Does this last theorem about P1 and P2, I missed it. Does it assume that M doesn't have large uniform minors like that?
It assumes something slightly stronger, actually, which is that M is ternary.
Oh, okay, yeah.
So I forgot to say, the U25 and U35 are not ternary, so this is a stronger assumption. You can prove something similar more generally for matroids without large uniform minors, but it's a little bit harder to formulate. Let me look at the chat box. All right, Sergey asks, are there any potential generalizations of Rota's conjecture? Yeah, I don't know. It's a good question. I don't know. Yeah, I mean, you could certainly ask sort of what is the class of pastures over which conclusion of Rota's conjecture would be true, but I guess that might be really hard. I'm not sure. Right, because this includes things like orientability, which we know the conclusion of Rota's theorem fails. Rota's conjecture fails. So I don't know what, what the criteria would be.
And is the question that you asked about tensor products and direct sums, is that the foundation of a 3-connected matroid is not the direct sum of the foundations of 2 other matroids? I just wanted to see if I remembered.
Right. So it's a theorem that the foundation of a 2-sum is the tensor product of the foundations. So if you have a matroid that's not 3-connected, then its foundation will break up as a tensor product. Now the converse is not quite true, but we think that it's almost true in a certain sense. I mean, you can see, for example, it's not true because the simplest counterexample would be you can tensor anything with the regular partial field and it doesn't change anything. It's like tensoring a ring with Z, it just doesn't do anything. Right, but just because you break up as that's why I said non-trivial tensor product. But I mean, there are more subtle counterexamples like that as well. But we think we have a conjecture that is true that would give a converse to this state. It seems hard to prove.
Thank you.
I was wondering if you could say anything about foundations of matroids represented over GF4 and orientable.
GF4 and orientable. Yeah, we've thought about that a bit. In fact, that's one of the next things that we wanted to try to nail down. So I think we have a conjecture about it, but I don't think we have a theorem yet. But I believe that should be accessible. And yeah, I mean, hopefully, I know there are some conjectures out there about quaternary orientable matroids, and I hope that these techniques would give a way to prove this. But I mean, we have to have a better understanding of foundations of matroids with large uniform minors that we don't quite have yet.
Yeah, so for these, I mean, seems possible that they'll all be representable, but it's there are conjectures that go both ways.
Yeah, right. I've seen that, and not sure yet what I believe, but what I think is the case is that there should be a finite list. This isn't an official conjecture, but I think there should be a finite list of foundations so that any map to F4 cross S lifts to one of those.
That would be nice.
And hopefully an explicit list. And they would include things like the golden ratio partial field, but there's other stuff too. But we don't yet know how to prove something like that.
So you said that F3 cross S can't be the foundation of any matroid. But do you think there's any hope of ever characterizing exactly which pastures are the foundation of some matroid?
I don't know. It's a good question. So I think there is some hope, but I might very well be too naive about this. Right, I mean, something that I guess it's related to what the strongest possible version of a lift theorem would be, right? So you, in partial fields, you can define this lift partial field. And if that is the universal partial field of a matroid, then you can sort of say stronger things. So we can define some kind of lift construction for products of, just for arbitrary pastures. You can have some kind of construction of a lift pasture that any map from the foundation to the given pasture would have to lift to the lift pasture. But if that construction doesn't always give something that's a foundation, then you have to keep iterating this and it could get hopelessly complicated. So the hope would be that maybe there's some definition of a lift that's actually idempotent, or at least has some nice finiteness properties. But I don't know whether to expect that that's true or not.
Okay, that makes sense.
Thanks. I'll go ahead and